Okay, so let me start. Thank you all for coming. So I wanted to discuss a bit on the kind of models we have been working on in trying to understand the high-redshift universe using the current and upcoming probes. So again, at the risk of repeating, let me again stress this point, which I think Andrei mentioned very nicely, that reionization is a multi-wavelength probe. So we now have access to a wide variety of different telescopes operating at different wavebands, which starts from NIR UV optical to microwave, that's the CMB, to the 21 centimeter signal eventually, which we want to detect, that's the ultimate low frequency probe. And this leads to serious challenges in trying to model this process. So the thing is, you need a model which has to incorporate nonlinear physics. So most likely you will be taking help of numerical models, and you have heard talks on such things. But these numerical models need to kind of simultaneously predict observables for a wide range of probes. And this leads to all these challenges like high dynamic range. You have need a very large simulation volume. At the same time, you may need to resolve very small spatial scales, very small mass scales, so that you know where the first galaxies were being formed. You need to solve for additive transfer, which is a very complex equation to solve. And then at the end, you realize that there is so much unknown in the high redshift universe. You probably need to run these simulations by varying your assumptions, varying your model parameters many number of times. So this parameter inference leads to the need for having very efficient kind of models, computationally efficient models. And this is where the semi-numerical simulations have played a very important role. Basically, what you are doing is you are making some approximations to model the large low resolution volumes efficiently. And there are a wide range of advantages to such models. You can do very efficient parameter estimation. You can, as I said, simulate large volumes which are required for these experiments which we have been discussing. And then you also need to kind of generate multiple realizations of the initial conditions to account for cosmic variance. Now, the thing I wanted to kind of discuss in today's talk are these three things. Basically, how do we model reionization sources? Because here you need to really talk about unresolved subgrid halos in cosmological volumes. I wanted to spend some time talking about the semi-numerical code we have been working on, named Script, along with the recent developments and extensions. And if I have time, I will talk a bit about how we are coupling this script to machine learning emulators for efficient parameter inference, which couples to some of these challenges which I talked about in the previous slide. So let's come to the first point. You have this large volume simulation, but you probably don't have the resolution to identify all the small mass halos where probably the first galaxies are going to form. So what do? You come up with some subgrid prescriptions. Again, in Andrei's talk, you heard one method of approaching this problem, and I will talk about a slightly different way we are trying to do. So essentially, what has been done in most of the semi-numerical codes is that you apply some analytical conditional halo mass functions in these low resolution volumes. Conditional because you need to condition on the local environment, which could be density. You can then become more adventurous and can condition on the tidal field or whatever you think is most relevant for modeling these halos. What we have tried, and this was a work done by Ankur Barsode, who currently actually is a student in ICTS doing gravitational waves, but at some point he was doing cosmology. And he came up with the idea of hybrid volumes. Basically, you run a very low resolution, large volume simulation, and you combine that with a small volume, high resolution simulation. So you identify the halos from the small resolution, and you find a way to match them to the locations in the low resolution volume and then populate this low resolution volume with the halos which are otherwise unresolved there. And he could show that we can recover the H1 power spectra to within 10%, sometimes much better than 10%, but most of the time within 10% of the true results, like a really high dynamic range simulation was run to compare the output of these hybrid volumes. Now, this still needs you to run like a coupled set of simulation. What we wanted to do is we wanted to see if we can give some kind of some formula, let us say, given your low resolution volume, the properties, I give you a formula to put in all the halos. Of course, you cannot give a closed form formula. That's probably not very easy. But in the age of machine learning, what you can do is you can try to find some non-trivial function which will tell you the mass function in these low resolution cells. So this is something we tried to do using Gaussian process regression. Again, the approach is quite similar, and we do achieve similar accuracy here. So the advantage here is once you do that, you can keep using it for future cases. You don't need to run this high resolution simulation again and again. Moving on, now we come to the generating ionization volume part. So what was known for quite some time that the conventional excursion set models, they don't conserve photons, and that non-conservation of photons depends on various factors. To the extent it depends on what kind of halos you are populating the source with, your resolution of the simulation, and so on. So this plot shows the amount of non-conservation versus the stage of reionization. And ideally, this quantity should have been 1, but you can see it can deviate based on difference, what kind of parameters you have in your simulation. But more importantly, what we were finding, at least with our excursion set models, were that these led to power spectra which were not converging at large scale. So depending on the resolution you use to run your simulation, your large scale power spectra were varying, were not the same. So this, when we are trying to kind of generate mock data and trying to recover parameters, we were seeing that unless we use the correct resolution which was used to generate mock data, we were getting biased results. So that led us to go to a different route for developing the semi-numerical simulations, which we call script, where we don't do it the excursion set way, but we just basically identify ionized regions around sources. When they overlap, we basically mark those cells as over-ionized, and we then redistribute the excess photons to nearby areas. So this is a broad idea. This was already tried in various other codes including, for example, Grizzly, which Raghu has been working on. And this code is explicitly photon conserving. It is slower than conventional excursion set, but still it's reasonably efficient that you can do parameter estimation. What is interesting is the moment you solve the photon conservation problem, photon non-conservation problem, this non-convergence of power spectra also gets solved. So the power spectra at low K, that is large scales, then become independent of the resolution you are using to generate the ionization maps. So this is why we spent some time developing this. And over the years, this basic version of our code script has gone through various extensions, and these are all people working on various aspects of kind of enhancing the semi-numerical code, where we have included now solving the thermal history, calculating CMB anisotropies, making predictions for Lyman alpha absorption. Akanksha was working on helium reionization. We are implementing cosmic dawn now, and so on, and also parameter inference. So with all these extensions, now we can model a wide variety of observations. And these are some typical applications which we did with this script. For example, we could model the Lyman alpha forest opacity fluctuations at redshift 5.5 to 6 and constraint reionization history. We could model the UV luminosity function, including feedback due to reionization, compute the IgM temperature, and try to match with observations again towards the end stages of reionization. We did quite a bit of work. This was led by my student Divesh Jain, who has completed his PhD, and so he was trying to see how much information we can get just from CMB data without having access to anything else. So mainly the CMB optical depth and the kinetics to Navier-Zeldovich effect. And again, the results were promising. He also went ahead and calculated the B mode polarization arising from patchy reionization, and that he showed that there could be implications depending on the nature of reionization and the amplitude of the primordial gravitational waves. It could have implications for the detection of so-called value of R, the tensor modes. And then, of course, I mean, once you have such a code, you can make forecasts for upcoming 21 centimeter experiments. And then we also, as I said, developed a machine learning technique for parameter estimation, basically emulators. And as I said, if I have time, I will go to that. The most recent enhancement is the subgrid modeling of photon sinks. So basically, if you want to compute quantities like photoionization rate and mean free path, where now we have measurements coming from Lyman alpha absorption spectra, we have to find ways to model these sinks, and they are essentially dominated by the self-shielded gas in these ionized regions. These, of course, will never be resolved in the kind of low resolution simulations we are running. So you have to do subgrid modeling, and preferably, I mean, that will be some kind of semi-analytical or analytical subgrid modeling. Of course, there exist analytical models which kind of compute these things, but like mean free path and photoionization rate, but globally average values. And for that, that is based on a model for the gas density probability density distribution. So this was like known for quite some time. In fact, I should mention here that when I was preparing this slide, it reminded me of a paper which I was reading. I read the first, which did a lot of reionization modeling, and that was by Chu and Jerry Ostraker, and we just had the sad news about Jerry Ostraker passing away. So it just connects to that as well. But coming back to the talk, what happens is, although these kind of models exist, what we need to do now is in the semi-numerical setup, we need to do the same modeling, but in each environment, let us say in each grid cell. So instead of having the full PDF, you need the conditional PDF. You have to somehow find a model for doing that. It just turns out that you only need the conditional PDF near the self-shielding threshold, and that self-shielding threshold is hopefully quite large. I mean, it will be only the high density regions which will be self-shielded. So we came up with a kind of very approximate model for doing that. Remember, while making the model of the conditional PDF, you also have to ensure that the so-called unconditional PDF, when you marginalized over all cells, you should be able to recover the underlying, the globally average PDF as well. So this is something which was done in collaboration with Anirban Chakraborty, my student. So he will speak on Thursday, but on something else. But this is something we did very recently. So once we did all this modeling, what happened is the various physical quantities in the model got kind of interconnected. So the although there is quite a bit of freedom in modeling the conditional density distribution, once you have modeled it, various things come out just by solving these models. And that makes the, I mean, the model in some sense quite inflexible. So then, given the model, what we try to see is there at least a sensible set of parameters which match the data which is available. It may, of course, we model the UVLF. This is not, I mean, this is not a very, I mean, you basically have to model the efficiency parameters appropriately so that you can match the luminosity function across a wide range of redshifts starting from 5 to 13. Now, this was already done by Anirban in an analytical setup, and that is something which we just implemented in the semi-numerical model. So Anirban will actually be giving his talk on something along these lines. And once we do that, we find that we need the galaxies to be forming stars more efficiently at high redshifts to match the JWST data. And also, at least to match the observations, we need the faint galaxies to be the main contributors of reionization. What happens because of all this modeling is various quantities, their spatial fluctuations get correlated. So in the same box, we will have emissivity fluctuations, which will be related to photoionization rate, the number of recombinations, mean free path, temperature, and so on. So it just comes out from the model. And then you can go ahead and try to model the redshift evolution of a wide range of observables. Of course, it matches the observations because we fitted the parameters to match the observations, but it was good to see that we have a set of parameters which match all the relevant observations which we were talking about. I'm not going through the panels in detail, but you can see there is a match with points with error bars. Of course, the next step would be now to vary the parameters and determine the range of source and IgM properties which are consistent with observation. So that is the parameter inference. And the moment you have such a model with a large number of free parameters, the conventional way of doing things becomes expensive, even though the models are reasonably efficient. What in this case, and again, this is something which is known in the cosmology and reionization community and is being used very widely, are emulators, and that is based on machine learning. So the idea is, imagine you have this parameter space. If you want to do the conventional parameter space exploration, you have to evaluate the model many number of times over a wide range of parameters. Instead, what you do is you basically evaluate the predictions in some predetermined set of parameter values and see if you can interpolate whatever you want to predict at all the other points. So this is the base essence of emulator. And as I said, I mean, all of us have interpolated in 1, 2, 3 dimensions using various available routines. The moment the parameter space becomes complex and high dimensional, you have to go to something much more sophisticated. And this is where the machine learning algorithms are quite useful. And what we have done already is we started with a GPR based emulator and more recently extended, currently extending is to neural network based ones, and we see already quite a bit of advantages in them. However, something interesting which we saw from the beginning is that, let us say you need to choose a training set, you will go to the prior and sample it in some way, and if we just take some again conventional way of sampling a parameter range like Latin hypercube, what you get is something which is shown here. Let us not worry about the parameters. Imagine there are free parameters of the model. The blue ones are basically what is you get from a true run of MCMC. So it is expensive, but you probably can run it and you will get something like this. All the other curves are basically obtained from the emulator, which is trained on a small number of samples chosen from a Latin hypercube sampling. And you see, I mean, looking at the contours, they look nice, but they were nowhere close to where the actual posterior is. What we also find is as we narrow down the prior more and more, they tend to slowly kind of approach the actual posterior. So what is happening is, if you, in the high redshift universe, when the model parameters are highly uncertain, you may start with a very wide range of priors. Now, if you are working with a very fixed number of samples, what will happen is it will lead to a coverage which is sparse. And this becomes particularly severe if your ultimate posterior is much narrower than the prior you started with. What may happen is in these high probability regions, you will have so less number of training samples that your emulator may not work. And that is what we were seeing in the previous example. So basically, you need to find a way to train the emulator in the high probability regions. But actually, you are developing the emulator to find out these high probability regions. So you have to break this circularity. This is again something which was known for a long time. And various techniques have been used in the literature. And this is just a few examples where people have run crude MCMCs to very quickly find the high probability regions and then do a more proper job there. Or you actually start with a narrower prior based on physical arguments. Or if you have run a previous MCMC, just utilize those chains to train your emulator, because once you have trained it, you can keep on using it. We were developing the models, so we didn't have access to many of these things. So we took a slightly different approach. What we did was, because our code is converged with respect to numerical resolution, we ran a simulation and did a MCMC with an extremely coarse resolution simulation. So this will be having grid sizes which are huge, but it will run very fast. It will take almost no time. You do that MCMC, that may not be the correct result, but it will roughly give you the regions where the probability is likely to be high. And then basically draw samples from the results of that MCMC run to do the training set. And this, interestingly, works very nicely. In fact, we first studied it a couple of years back on a GPR-based emulator, and we saw that we can very easily get 30 times speed up compared to like MCMC done with full simulations. And as I said, this is something which we can still do with a less number of parameter, with a model with a less number of parameters. This will be very difficult with our like more recent extensions where the number of parameters have increased drastically. So we got a 30 times speed up. Now we are extending it to neural network based simulators. And now we are getting another order of magnitude speed up. So we can really do these things quite fast. But as I said, the trick here is to make sure that we choose the training set carefully. Otherwise, this won't work. At least our approach won't work. So that basically brings me to what I wanted to talk about. I'm trying to convince you that modeling reionization requires like very high dynamic range simulations if you want to do it like very rigorously. So you need to model large scale structure, galaxy formation, radiative transfer, and so on. The alternative is to go for semi-numerical models. So I have kind of discussed the photon conserving model which we have been working on, that is script, and it enables efficient modeling across a wide range of observables. I also did discuss a bit about emulator-based inference, both based on GPR and ANN, which accelerates parameter estimation, and that is basically essential for leveraging the data sets we have and what we will have in the near future. And we are still trying to like improve and enhance the model, for example, by refining the subgrid physics and like anchoring the models to a wide variety of observations. So I will stop here and take questions if any.
Thanks. We have a few minutes for questions.
Yeah. Thanks for the talk. I was wondering if you can elaborate a little bit more on this claim about the converging with like low resolution, because this doesn't make sense to me. Like I mean, in the limit, you know, your whole box is one cell. Reionization is a step function, right? And the power spectrum is a step function. Like you need. The reason why we can model reionization is because we're essentially resolving the fluctuations in the emissivity and the fluctuations in the recombination rate and how they couple together, right? So it shouldn't converge because you as you go to larger cells, you're missing, you know, your Nyquist frequency limited by missing the fluctuations in the emissivity and the recombinations.
Yeah, okay. The first point is even if the whole box is a cell, reionization need not be a step function because even 21 centimeter fast and our code deals with partially ionized cells. Yes. In that case, Q will be exactly equal to zeta F collapse, accounting for recombinations and other things.
But that's
yeah,
a subtlety though. That's a subtlety though, because it's a different kind of way of calculating it. That's a subgrid way.
Yes.
The actual way of like this cell is ionized versus not, it would be a step function.
Yes.
That's another like correction, but yeah.
So yes, you're saying but that goes into this non-convergence of power
And that
spectrum.
one doesn't include recombinations, just usually in
Yes,
the way that.
so let us again do it in steps. I mean, suppose in the idealistic case, when you don't have recombinations, you expect the low k part to basically converge to the same value as long as those k modes are much smaller than the grid resolutions you are talking about. So suppose you take two grid resolutions of, let's say, 2 megaparsec and 4 megaparsec, and you go to something like 50 megaparsec, you should see you expect the power spectra to converge at that scales.
That's true if both of those grid resolutions essentially resolve fluctuations, the spatial fluctuations of your source field and your sink field.
Yes, yes, exactly. So the claim is that, so suppose I leave aside the sink field for the time being, I agree that it needs to, if it cannot resolve, then you need to model the source field correctly, accounting for the subgrid part. So essentially the point is that if you don't have converging power spectrum at low k modes, if it depends on the resolution you used to run the simulation, then for actual data, you will never know which resolution to use. So you better have something which kind of converges. With our new subgrid model of sink, I mean, we can show that even in the presence of sinks, the large scale power spectra does converge.
So I mean, just to clarify, we do see like convergence in like our, fiducial setup. We see some kind of convergence, but we don't explore crazy, like this is because like the source models that you use for test convergence generally are resolved by like these level of cells. If you go up to like, crazy cell sizes or small, you shouldn't see convergence unless you have a
okay.
correct
What I'm
subgrid
talking
description.
about is
But
slightly
anyway,
more
it's-
subtle. I mean, we can
I think
discuss.
it's a subtle discussion. but
Yeah,
we can discuss it.
because I mean, even if you start with a source model which is well resolved, let us say you start with a proper n-body simulations where all halos are resolved, but you generate the ionization fields at two different resolutions. What we were finding is the excursion set doesn't give power spectra which are converged at large scales. So it has to do with the excursion set.
Just to clarify, your implementation of excursion set, just to clarify.
We can check.
Yes.
We can
I
check
mean,
with the
we-
21 centimeter fast. We
we
have
did
shown
that.
that it doesn't work with 21 centimeter fast as well, at least with the public version. I cannot comment on anything beyond that.
Yeah, I hope this and other questions we can take up at lunch break. Let's thank the speaker again.